In this video, we're going to learn about pins and rollers for a truss and the reaction forces that they provide so that our truss is nice and stable. And we're also going to learn about static determinacy, which is a quick calculation that we can do to see if we can even solve a truss before we do it. So let's get into it.
So let's talk about free body diagrams just to refresh our memories a little bit. So a free body diagram or a force diagram is just a representation of the object that we're focusing on and the forces that are interacting with it. Now in physics, we usually think of them as point masses, so little tiny dots, but especially when dealing with trusses, we look at it as an overall body. So we're ignoring all other forces except for the ones that are acting specifically on our truss. Now when we get into it, we're going to need to be really specific on how we draw our free body diagram. So this is an example of a truss that we will solve later on, where we have lots of dimensioning, we have angles, we're going to know the magnitude of these forces. So it's important that we are extremely precise with our force diagrams because we're going to have to break down every single one of those forces to solve for it. Now what we're going to focus on for this video is the reaction forces provided by the bridge. And there are two big types of support reactions that we're going to deal with. Now there's lots of them that are going to be handled with bridges. So there's going to be tension from cable supports. There's going to be cantilever supports. But we're going to focus on two. We're going to focus on roller support reactions and pin support reactions. And when we name these, we're going to identify them by the joint that they're located on and the direction that the force is moving. So let's talk about our first one. Let's talk about the roller. So we have a good example of a roller right here on the bridge. And notice how literally we have little rollers right here where it's allowing us to move a little bit in the horizontal direction. And the way that we represent that in a truss is by a circle kind of representing that roller, or sometimes we'll see like 3 circles or something like that. So as long as you see the circles, that represents a roller where we have a little bit of movement in our X direction. Now when we're turning that into a force diagram, we are going to replace that with one reaction force which is perpendicular to the surface. So what that means is our rollers allow us to move in the X direction left and right, but they provide a force pushing up or down on our bridge. So if I were to translate this into a force diagram, it would look something like this, where I am replacing my little circle for the roller for a force that is moving in the Y direction. That is perpendicular to my surface. And so we're going to name that based on the joint that it's on and the location that it's at. So we're going to call this force RAY. So R tells us that it's a reaction force. A tells us that it is acting upon joint A, and Y is telling us that it is in the Y direction, or the up and down direction. Now technically we don't know if it's up or down, but later when we do calculations it will kind of tell us that. So for now we can just have it pointing up. So a roller we are replacing with one force perpendicular to the surface. Now let's talk about the second one that we're concerned with, and that is a pin. So notice how a pin really locks down our bridge. And we're going to represent that by a triangle. Now a pin is a little bit different. That is going to provide two reaction forces for us. So it's going to give us a reaction force in the Y direction, but it's also going to prevent our bridge from moving in the X direction. So while rollers give us support going up and down, pins give us support left and right and up and down. So if I were to translate this truss over here into a force diagram, it would look something like this on joint A, where we have a horizontal force and a vertical force. So now we just have to name those guys. So we have RAX, which represents a reaction force acting on joint A in the horizontal or the X direction. And we are also given RAY, kind of similar to what we did for the roller. So we have a reaction force on joint A but this time in the Y direction. So notice how we name those based on their joint and based on the direction of the force. Now, one thing that's kind of odd to us is why the heck do we even need roller supports? Why don't we just use pin supports and make sure that our bridge is locked down? Well, if you think about bridges, there's a lot of forces acting on a bridge, and not all of them can necessarily be accounted for. So think about if you have a really windy day. If your bridge is too rigid, things could snap even in a really high wind. Think about like a skyscraper. Modern skyscrapers are meant to kind of bend and sway a little bit, and you feel it when you get up top because that flexibility allows us to kind of bob and weave with the wind. Now, especially in Iowa, if we had like a roller support up on top, we have kind of this joint here, especially in places like Iowa where there's drastic temperature changes. When it gets really cold, things shrink. When it gets really warm, things expand. So we, as engineers, we need to take that into account in the designs that we're doing. And rollers are a really nice way to kind of account for a little bit of leeway with the forces acting on our bridge. So again, for our support reactions, if you have a pin, you're going to replace it with one vertical and one horizontal. Whenever you have a roller, we're going to replace it with one reaction force that is perpendicular to the surface. Now keep in mind, we may have pins and rollers on a vertical surface, but think about it as more of perpendicular and parallel to the surface rather than always up and always down, or always left and always right. Now again, we don't actually know what direction these forces are going to act, whether it is up or down or left and right. But the calculations that we create are going to solve that for us later on. But we'll see that in future videos. So let's see if you can figure it out. What I would like you to do is in your notebook, pause real quick, and I want you to draw this truss as a free body diagram and replace the pins and rollers with their proper support reactions. So take a second, pause, see if we can get this right. Did you pause? All right, I trust you. Let's check it out. So we have a roller over on the left-ish side, and we know that always gives us a force that is perpendicular to our surface. So in this case, we have a reaction force acting on joint C in the Y direction. And if I replace my pin, I have a reaction force on joint G in the Y direction, but also a reaction force on joint G in the X direction. Now let's finish this thing up by talking about static determinacy. When we're solving these trusses, the first step that we really need to do is figure out, can we actually solve this thing? So if your truss is statically determinate, that means that you can actually solve it. There are enough knowns where we can figure out the reaction forces, the internal forces, the angles, all that good stuff. If not, then we're in trouble. So we have this equation, 2J equals M plus R, and what that is representing is J represents the number of joints within your truss. So that is where members and reaction forces meet together. M is the members, or kind of the straight pieces of your bridge. And R is the number of reaction forces from your pins and your rollers. So if your left side and your right side are equal to each other, we know that we can solve that truss. That means it is statically determinate. So let's see what that looks like. Let's say that we have a truss right here, and it might be a good idea to copy this down so you can check it out later on. So we need to solve for the number of joints, the number of members, and the number of reaction forces. So let's go ahead and do that. If I'm looking at my truss, a joint is anywhere members or support structures are going to meet up. So we have 1, 2, 3, 4 joints in our truss. So I'm going to toss that into our equation down there. Members are the straight beams within our truss itself, and they're always separated by joints. So if you look at the member from A to C. That is not one member, that is two members, one right here and one right here. So let's count those out as well. We've got A to D is 1, A to B is 2, B to D is 3, D to C is 4, and B to C is 5. So we have a total of 5 members going on there. And then last but not least is the reaction forces. We have a pin over on the left side. We have a roller on the right side. So if I replace those, we have a vertical and a horizontal force from our pin. We have a vertical force, or excuse me, a perpendicular force from our roller, which means that we have 3 reaction forces. So if we calculate those up, 8 equals 8, which means yes, this is something that we can actually solve for in our truss solves. So let's have you try one out for yourself. Go ahead and copy this down in your notebook or a scratch piece of paper. Pause this video, and I want you to figure out, is this truss statically determinate? We have a pin on the left and on the right side. See if you can figure out the joints, the members, and the reaction forces to see if it's statically determinate. Did you do it? You did a little bit quickly. All right, let's check it out. So I find that I have 4 joints, 1, 2, 3, 4. I have 5 members, 1, 2, 3, 4, 5. And I have 4 reaction forces, 2 from each pin. So 8 is not equal to 9. So what that means is this truss is statically indeterminate. No matter how hard you try, you're not going to be able to solve this truss. And that is a big problem. So as engineers, what we need to do is we need to figure out how can we modify this truss to make sure that it can be determined. So if I think about, there's a couple things I could do. I could kind of increase things on this side, but especially since we're multiplying things, I can't really put a joint there to make things even out. So I probably have to mess around with something over here. And probably my best bet is I don't want to take away a member because that'll make my truss a little bit sketchy. Maybe if I mess with those reaction forces, I can make things even out. So what I'm going to do is I'm going to replace one of those pins with a roller. So I'm decreasing the amount of reaction forces that I have. So if I were to recalculate, I've got 4 joints, I've got 5 members, but now I have 2 forces from the pin and 1 force from the roller, which means yes, 8 equals 8. We can solve for this truss.